Hey everyone, it's me from the future. This video is pretty long. It turned out to be about 20 minutes, so feel free to skip around. The first 10 minutes teaches you how to do part A, and it's just rinse and repeat for parts B and C. So just watch the first 10 minutes to get the basic gist of the problem, and then watch the last few parts where I show the answers so you can check your work if you don't want to watch the whole 20 minutes. Thanks. Question 41 reads, a force acting on a particle moving in the xy plane is given by F equals 2y I hat plus x squared j hat newtons, where x and y are in meters. The particle moves from the origin to a final position having coordinates x equals 5 meters and y equals 5 meters as shown in the figure. Calculate the work done by F on the particle as it moves along path OAC, OBC, and OC. And lastly, explain, is F a conservative or non-conservative force? And so this is the diagram. Let's start by drawing our diagram. So part A wants you to find the work from O to A to C. So let's start by finding the work from O to A. So you know that your equation for work is work equals integral of F times dr. So you are given F, which is 2y I hat plus x squared j hat, but you don't know dr. So what you're really trying to do is find dr. But dr is the derivative of r, so you need to start by finding out what is r of t, then you can take the derivative of that to get your dr. So you can find r of t, or your position vector, by using this equation, 1 minus t r naught plus t r1. And so t is your variable and r naught is simply your starting position, which is 0, 0. And r1 is simply your end position, and in this case we end at a, so 5 comma 0. And so you just plug it in like so. You do 1 minus t times 0, 0 plus t times 5, 0. And so you can see here that 1 times 0 gives you 0. So this first part, the component vector is just 0, 0, then plus 5t, 0. So you add them together literally, so you get 5t in the x, and then 0 for the y. So once you have this is your rt. You want to take the derivative of this, so you do dr over dt. The derivative of 5t is simply just 5. And so you can multiply both sides by dt. dr is 5 comma 0 dt in component form. So now that you have dr, you can go ahead and, before you use your work equation, you need to find, you might as well plug in, y and x for f. And so I'm just gonna rewrite it. Your y in this situation is going to be 0. When you plug in x and y for your force vector here, you want to plug in these two. This is your x value, and this will be your y value. And so you can see that 2 times 0 is going to be 0, plus x squared, 5t squared, 25t squared. And so this is your force. And you're gonna do, let me rewrite that. It's gonna be 0 I hat comma 25t squared j hat, which you can then rewrite it into the form, into a component form to make it easier, 0 comma 25t squared. So now you have f and you have dr. With these two, you can plug it into that equation and we can solve this. So work equals integral. And every time you use this equation to find your r of t, it's always going to be in this restriction. I forgot to mention that earlier, but every time you use this, it's always going to be between 0 and 1. And since it's going to be between 0 and 1, down here, it's going to be from 0 to 1. And so you plug in f, which is what you found out here. It's going to be 0 comma 25t squared. And then you're going to do a dot product with dr. And in this case, dr is 50 dt. And when you do a dot product, you just multiply, the first terms by each other and the second terms by each other. And so you'll see that 0 times 5 gives you 0. 25t squared times 0 also gives you 0. And so you could go out and find the integral, but it's pretty obvious here that work from O to A is simply 0 joules. And so now what we need to do is find the work from part A to C. And so keep in mind, the A position is 50 and C is 5. So let's make note of that on this page. A is 50, or this would be your R naught when you find your position vector, when you find R of T. And your R1, when you use that equation, will be 5. So let's begin. It's going to be the same process as before. You start by finding R of T. And so R of T, we're going to use this formula again. 1 minus T R naught plus T R1. And this time we're going to remember to restrict this. 0 like that. So you plug in R naught, which is 50. Then you plug in R1, which is 5. You multiply and you find that you get 5 minus 5t, comma 0 plus 5t, comma 5t. And so what you want to do is literally add, the first term. So 5 minus 5t plus 5t gives you 5, comma 0 plus 5t. So your position vector is this. But now you need to get the derivative of that. And so dr, and I'm going to just multiply dt, save a step there. But the derivative of this is going to be 0, comma 5. Now you have dr. Let's find F, or the force. And we're just going to plug in this in the x value and this for the y value. And so our force was, given by the problem, 2y I hat plus x squared j hat. So 2y, we will end up getting 10t squared I hat plus, and for x you plug in 5 squared plus 25 j hat. Let's rewrite this into component form, and that basically means you just don't write I and j. So that's 10t squared, comma 25. So you have F, you have dr. We can plug it into our work equation. So work equals integral from 0 to 1, F time dot product dotted with dr. And so we are going to plug in F, which is 10t squared, comma 25. Oh, I forgot to write plus 25. And then dotted with dr, which is 0, comma 5. And yeah, for the previous problem, I should have written a plus there. But yeah, I kind of screwed up. That plus sign shouldn't be there, and it doesn't really matter in this problem. The work is right, though. Just keep following it. Let's move on. Let's multiply that. You will get 0, comma 25 times 5, 125. So now that you're here, what you can do is find the antiderivative of 125. But since, it's a constant or it's a number, the antiderivative will simply be, 125t. You do this. And so once you find the antiderivative of that, you will put it here and write it like this. And so to solve this, you plug in 1 for t, and then minus 0 for t. So you just take 125, plug in t, this minus what happens if you take 125 times t, 0. But in this case, it's just 125. And so the work from A to C is 125 joules. And so the total work from O to A to C is 0 joules plus 125 or simply 125 joules. And this is part A. Alright, so part B wants you to find the work from O to B to C. So let's start by finding the work from O to B. And so the process is going to be exactly the same as before. So if you want to see the worked out solutions, just go to the end of the video. But if you want to see me work it out, just continue watching. So again, we're going to find out R of t, and we're going to use this formula, 1 minus t R naught plus R1, t R1. And so your starting position is going to be 0, 0. And your final position is going to be 0, 5. So let's plug those in. 1 minus t 0, 0 plus t 0, 5. And so you'll get, this is just going to turn it to be 0. And this is going to be, this is going to be 0, 0, and then plus 0, 5t. Add these two together. Your R of t is just 0, 5t. And so now you have that. Let's take the derivative of this. And so the derivative of 5t is simply 5. This is your dr. Let's find out f. Let's just plug it in. We're going to plug in this for x and this for y into our force vector, which is 2y I hat plus x squared j hat. And so x for y will do 10t I hat plus, we're going to plug in x right there, so that's just going to be 0 j hat. Let's rewrite this in component form, 10t comma 0. Now we have f and dr. Let's plug it in once again. It's going to be from 0 to 1. This is our f. And we're going to dot it with dr, which is 0, 5. So let's multiply these two. You'll get 0 and 0 again. And it clearly turns out to be just 0 joules from O to B. So now let's find the work from B to C. And so let's keep in mind our R naught now will be 0, 5, and now our R1 will be 5, 5. And so let's make note of that right here. R naught is 0, 5, R1 is 5, 5. Let's begin. Once again, R of t. Let's use this formula again. 1 minus t, R naught plus t, R1. Let's plug it in. 1 minus t, R naught, 0, 5. And then plus t, R1, 5, 5. Let's multiply these. And you will get 0. You do 1 minus t times 0, so that's just 0. And then 1 minus t times 5, which is 5 minus 5t. And then you're going to add it with 5t, comma 5t. Once you add these two, you will get R of t is 5t, comma 5. 0 plus 5t gives you 5t. 5 minus 5t plus 5t gives you just 5. Now you have R of t, your position vector. Let's find the derivative of that, which is derivative of 5t is 5. Derivative of 5 is 0. And now you have dr. Let's find f. And we know f is, given by the problem, 2y I hat plus x squared j hat. You plug in this for x. You plug in this for y. 2 times 5, 10 I hat plus x squared, or 25 t squared j hat. So let's rewrite this in component form. You have 10, comma 25 t squared. And now let's plug it into a work equation. Integral from 0 to 1, f dotted with dr. Let's plug in f, 10, comma 25 t squared. Dotted with dr, which is just 5, 0. And so let's multiply these. 10 times 5 gives you 50. 25t squared times 0 gives you 0. And so, what is the integral of 50? Well, it's just 50t. Now you can do this thing. So, you're going to do 50t times 1 minus 50t times 0, which is just 50 joules in this case. Work is 50 joules. So the work from B to C is 50 joules. And the work from O to B is 0. So your overall work from O to B to C is just 50 joules. And that is part B. Okay, finally, we're finding the work from just O to C. So let's do that. O to C. Now, once again, we're going to find R of T using this formula. 1 minus T R naught plus T R1. This time R naught is 0, 0. And your R1 is 5, 0. So let's multiply 1 minus T by 0, 0 plus T 5, 5. So that just turns out to be 0 plus 5t, 5t. And that is R of t. Let's add them together. R of t is just 5t, 5t. And so let's find the derivative of R over t. Derivative of that will simply be 5, 5 dt. Now that you have dr, let's find f. Let's just plug it in. You're going to plug this for x and that for y. So 2y I hat, this is given by the problem, plus x squared j hat. 2 times 5t, you get 10t I hat plus x squared, or 25t squared j hat. Let's rewrite this in component form. F is 10t, comma, 25t squared. Let's plug it into our work equation now. Work equals integral from 0 to 1. You're going to plug in f, so 10t, comma, 25t squared, dotted with dr, which is 5, 5. Let's multiply these out. So 10t times 5, this is 50t, plus 25t squared times 5, or 125t squared. Now let's find the integral of 125t squared and 50t. To find the integral of 125t squared, we will do this. We'll put t, and we know the integral has to be, to the power 3. And so what times 3 will give you 2? And that is 1/3. You want to take 1/3 of 125t squared. So you'll do 125 divided by 3t cubed plus the integral of 50t. Integral of 50t will actually be, well, half, because when you do the power rule, 2 times half will give you 1, which will give you, back to where you started from. And so up here, to check that, t, when you do the power rule, you'll get just t squared. So you will do 50 divided by 2, t squared, from 1 to 0. And so when you do this, you will take 125 divided by 3 times 1, which is just, 125 divided by 3 plus 50 over 2. And this will give you your work from O to C. Let's plug it into our calculator.
125 divided by 3 plus 50 divided by 2.
200 divided by 3. This is your final answer, 66.7 joules. So this is your final answer for part C. The work from O to C is 66.7 joules. And that is part C. And that's it to problem number 41. I almost forgot to do part D. Part D asks, is F a conservative or a non-conservative force? Well, the force is actually non-conservative as you solve the entire problem. The work done in each path is different. Therefore, therefore the force is non-conservative because it is path dependent. So if I were to write it out, F is non-conservative because the work done is path dependent. That's part D. Here's all the work. This is part A. First page of part A, if you want to see that. Second page. And here's part B. First page of part B. Here's the second page of part B. And here's part C. Hopefully this helped you. Thanks for watching.